magnets. Magnets always have a north and south pole, even if they get cut in half. Remember from February, when on Valentine's Day we had class and we talked about the scientists at Stanford? There's no such thing as magnetic monopole. So even if you cut a bar magnet in half, each half becomes its own bar magnet. And no matter how small you made them, you'd still always have two poles. There are some objects that are magnetic. Some of them are permanently magnetic. Others can be temporarily magnetized, but eventually lose their magnetic fields. So, we've played with magnets. Can there ever be a liquid magnet? Turns out the answer is no. Because a liquid is very disorderly, it's disorganized, there's no way for all the little magnetic domains to align and actually create a magnet. So, permanent magnets you might be familiar with. There's a bar magnet, a horseshoe magnet, a compass. Alright? And then things that you can magnetize are things like paper clips, iron filings, and nails. Magnetic force. We'll talk about equations later, so for right now, we're not really worried about that. We're worried about concepts. So what you probably already know. Opposite poles attract and like poles repel. This is similar to when we did electrostatics, and we had like charges repelled and opposite charges attracted. If you have a magnet in a magnetic field, it will align with the existing field if it's allowed to do so, if it's free to move. So, talking about that, okay, a magnet in a magnetic field will feel a force to align with the field. For example, that's really what a compass is doing. Alright, the north pole of the compass wants to align with the field lines around the Earth. Because all magnets are dipoles, meaning they have two poles, they will experience torque until they do align with the field. This is actually the lab that we did in class on Tuesday. You used a compass to trace the magnetic field of a bar magnet. You maybe didn't put it at quite as many points as this, but I think you can kind of see what you got in class. So you can see that every location the compass points in the direction of the magnetic field, and it's different everywhere you go. So if you were actually going to draw the field lines, you would get something like this. Alright? You'll notice the lines leave out of the north pole of the magnet and enter the south pole of the magnet. Alright? And then all of them make a loop. They're always loopy. Now, the ones that are directly horizontal, they look like they don't ever reconnect, but really, they do. It's just so big of a loop you can't see it. Okay, just like we had rules for electric field lines, we have them for magnetic field lines as well. Okay, first of all, they always point out of the north pole and into the south pole, outside of the magnet. Inside, like we saw in class, the field lines go from north to south. The closer together the lines are, the stronger the magnetic field is at that point. This is the same as with electric field lines. Again, field lines never cross. And magnetic field lines always form a loop. Although, as we saw in class and in the slide before, very often we don't draw the field lines inside the magnet. Okay, so magnetic field has a unit. It's actually called a Tesla. Yes, same guy as the Tesla coil. 1 Tesla is a huge amount. The Earth's magnetic field is on the order of 3 times 10 to the negative 5th Teslas, or about 30 microteslas. Not very much, really. Okay, so speaking of Earth's magnetic field. Alright, some of you talked about this in class. If the north end of the compass points to the south pole of the Earth, is our system backwards? Kind of. So, the north end of the compass points towards Earth's magnetic south pole, so it points to our geographic north. So you'll notice in the picture here, the geographic south pole is actually very close to the magnetic north pole, if you're going to think of the Earth as a bar magnet. Okay, but that magnetic field in the Earth is not actually quite aligned with the geographic poles. This is called declination. Okay, so to get the number, it's the number of degrees difference between the geographic pole and the magnetic pole. So that's why if you're doing orienteering, you go out hiking, you take a compass, the magnetic north will differ slightly from the geographic north by different amounts depending on where you are. And where those poles are shift over time. You can see in this graphic that the poles are constantly shifting. Alright, so in summary, there's only a few points. Magnets have two poles. Always, one north, one south. If there's a magnet, there's a magnetic field around it, and magnets in a magnetic field will experience a force. That's really it. And make sure you kept your notes, because there'll be a quiz tomorrow.